For my project, I chose kinematics from a historical perspective. I chose this topic because it's intriguing to me how diverse kinematics is and how foundational it is as a subfield to the rest of physics. Because it's so foundational, kinematics can be as easy or complicated depending on what field it's utilized in, such as medicine to astrophysics. There aren't many subjects that have an influence on so many different fields, and this stood out to me because it does. One of my goals for this project is to exhibit scientists that aren't talked about too much in the Physics 1 setting, but have a strong influence on topics covered in class. I also want to go over additional topics that closely tie into kinematics, but are not covered in the curriculum. Before we look into specific examples, we need to understand what kinematics actually is. The word is derived from Greek and means movement or motion, which is essentially what is being studied. It describes the motion of objects or systems without considering forces that are acted on it. It is part of classical mechanics, which means the past and future state of an object can be determined if the present state is known. It ties in with geometry, and a lot of missing information can be solved using geometry, as we will later see. The founder of kinematics is Galileo Galilei, and was born in 1564 in Pisa. He was an astronomer, physicist, and engineer. He is also considered the father of modern physics. A lot of his work aimed towards discovering the mechanisms of speed and projectile motion. Galileo also derived kinematical theories, and we will look into a specific example here. Let's say that line segment AB represents some time interval, CB is the greatest change in velocity of an object in that time interval, and AC is the relationship between the change in velocity and time. What we have here is a variation of a modern velocity time graph. Because of this, the area of the triangle would be the displacement of the object, just like the area under the curve of a velocity time graph. The theorem states that the time in which any space is traversed by a body starting from rest and uniformly accelerated is equal to the time in which that same space would be traversed by the same body moving at a uniform speed whose value is the mean of the highest speed and the speed just before acceleration began. We can draw a rectangle in the triangle as seen here, and line segment BD is the midpoint of CB, in other words the mean of the highest speed. FD is constant velocity or uniform speed. We can see that the green triangle DCE is equivalent in area to the blue triangle AFE, and trapezoid BDEA is shared among both objects. Because of this, both objects have the same area and therefore the same displacement. This shows how geometry can be used to solve kinematics problems. Let's move on to Isaac Newton. He was born in 1643 in England. He is regarded as one of the most influential physicists of all time and worked on topics directly related to Physics 1, such as the three laws of motion and gravity. A lot of phenomena studied by other scientists inspired him to physically express them, such as Kepler's theory of planetary motion, comet trajectories, and equinoxes. A lot of his findings influenced the Industrial Revolution. Johannes Kepler was born in 1571 in the Holy Roman Empire. He was an astronomer, mathematician, and astrologer. His belief that God created order in the universe was a primary motivation to study the cosmos. He developed the three laws of planetary motion, one of which being that planets revolve around the sun in an ellipse. Let's see how Newton's and Kepler's ideas tie together. In Physics 1, we focus on force and kinematics occurring in the same direction, but what about when they occur perpendicular to each other? Newton found that circular motion is created when velocity and force share this relationship. Velocity is tangent to the circle, and force is directed towards the center of the circle. This is centripetal force. This same concept can be applied to Kepler's model of planetary motion where the centripetal force is equal to gravity. Also using Kepler's model, Isaac Newton came up with the concept of escape velocity. This is the minimum velocity required for a revolving object to escape the gravitational influence of another object. Here is a worked out example of the moon's escape velocity. Notice how the velocity depends on the Earth's mass, but not the moon's mass. Isaac Newton also derived an equation using the centripetal force. With this equation, the centripetal acceleration can be found using F equals m8. We can equate both equations, cancel mass from both sides, and solve for acceleration. Here is a demonstration of this example using figures. Centripetal acceleration will point in the same direction as centripetal force because of Newton's second law, and this shows how force can connect to the field of kinematics. Here are the references I used to create this project.